Good day, ladies and gentlemen. This is the second lecture of the series of lectures introducing the RM software for filter design. In this lecture, we will give you an overview of the solution technology offered by the RM software. Here is the content of this presentation. It is in fact a list of possible physical realizations offered by the RM software. First is parallel infinite impulse response digital filter realization obtained by the bilinear transform of analog prototype. Then comes parallel realization of switched capacitor version, again obtained by bilinear transform. Then parallel realization of analog active RC version, cascade realization of analog active RC version, passive LC cascade realization, and the group of operational transconductance amplifier C or GMC realizations, the first one being the passive LC being based on passive LC prototypes, then parallel realization of single and double phase filter with introduction of polyphase filtering shortly, and finally cascade realization of GMC filters, which is analog to the RC counterparts. We will start with the program IIR parallel, which performs synthesis of digital infinite impulse response filters or recursive filters. It produces a final solution with full accuracy, 16 and 32-bit accuracy of the coefficients of the system functions, which are here on the right-hand side shown within the schematic, which is general, which means may be implemented for even the top two parts, and odd filters, all three parts. The bottom cell is first order cell. As one can see, the RM software is synthesizing only parallel realization of recursive filter, since it allows for stability to be preserved when bilinear transform is used. The program produces several files as a final solution, which are a report file containing the complete report, all the calculations, including the pole zeros of the untransformed, the transformed filter, and the values of the coefficients, the process of evaluation of the coefficients, and so on, while also it produces a HTML file where, in addition, the schematic may be reconstructed. The RM software is performing synthesis of switched capacitor filters. It is done by the program SC parallel, which means the solution will be a parallel connection of cells which are driving a summing amplifier. We can see here the general schematic of the system, which means that an analog voltage source is used to drive a sample and hold circuit, allowing the processing of the pulses produced. Then a set of parallelly connected cells are implemented, and the result, the outputs are summed to produce the output signal. Due to the presence of switching, the output signal is full of sharp changes or harmonics. So for the filter to be completed, one needs the so-called anti-aliasing filter to be added at the output, which is not shown here. Here is one of the cells which are connected in parallel. This is a second order bigwood implemented for the case when the poles of the cell have a high quality factor. This program delivers a report file which is following the complete synthesis process, starting with the poles of the original analog filter, then produces a HTML file which contains, in addition, schematic, all the cells which are implemented, including the summing and including the anti-aliasing filter and sample and hold filter too. And finally, it produces a SPICE code or SPICE net list for time domain simulation. This schematic contains non-ideal switches, which are natural for SPICE, which have a finite on and off resistances, which may affect both the simulation run as such, so the simulation may be stalled, and also partly because of the finite element of the resistances, partly it may affect the results, the waveforms. Next is the parallel synthesis of active RC circuits, which is performed by the RC parallel program. Here is the schematic of the overall system. This is the structure. So the analog source is driving a set of parallelly connected cells, which are second order, except in the case when the filter is of odd order and then one of the cells is first order. Then comes the summing amplifier, and no need of anything else is necessary. What is important here to note is that some of the cells have negative gain and some have positive gain, and that may be in contrast to the sign of the gain of the transfer function of the cell. So the summing amplifier performs also inversion of some of the signals to produce a proper summing. Here is a cell, second order cell, which is used in parallel. And it is important to have in mind that all second order cells are low pass and have 1, 0 at the real axis. And the structure of all the second order cells is the same. Only the element values are changed in parallel realization. And that is a very nice property from the programming of the synthesis program point of view. It is really simple. So there is a first order cell, and there is a second order cell with two variants of high quality factor of the pole and low quality factor of the pole. Altogether 3 cells, and that's summing amplifier. Here the deliverables are also a report file containing the whole process of the synthesis, the .html file which contains also the schematic, and SPICE code for frequency domain simulation. Since it contains only linear circuit elements, by simple modification of the excitations and the simulation type comments, one may produce a time domain simulation by the same file with not much effort. Next is the cascade realization of active RC circuits, the structure of which is given here. So there are cells connected in cascade. The crucial thing here is that every active cell has at its output the output of a operational amplifier, which means that the output resistance of every cell is negligible, which then means that the transfer function of the cell is not changed when loaded. So the cells are not loading each other. And simply what is done mathematically when creating a transfer function as a product of biquads, here the same is transposed directly, and the gain is a product of the gains of the cells. A wide variety of cells has to be developed for such a program to be effective. Here is an example where a notch or band stop cell, which is symmetrical, which has symmetrical amplitude characteristic, is shown. As one can see, there are large number of circuit elements, which means in general cascade realization may be quite a complex circuit all. And again, one gets a report file containing the whole process of synthesis, the HTML file containing the schematic and the whole process of synthesis, and SPICE code for frequency domain simulation, which may be, with a small effort, transformed into a SPICE code for time domain simulation. Next is the passive LC cascaded realization. Here, a cascade of cells containing capacitors, inductors, and transformers, potentially, are used. It is the most difficult problem of synthesis of filters, since, as one can see, the cells are of variable complexity, which is expressed here with the number of new nodes introduced by the cells. And the cells are loading each other, which means that during the synthesis process, one have to take care of the resulting of the rest of the cells, which will load the previous one which was synthesized, and that is both numerically and from the programming point of view very difficult problem. Also, since the number of type of the transmission zeros which are extracted with every single cell is large, so there is a large variety of cells which should be programmed for synthesis. Due to the fact that it introduces numerical problems when calculating the rest of the impedance while one cell is extracted, this program is written with long double or double accuracy to prevent numerical errors, and as will be seen later on in different slides, not always is possible to avoid numerical burdens which are introduced in this synthesis. The Cascade LP program implements a special transmission zero extracting procedure to assure reliability. And that means that the order of extraction of the zeros may affect seriously the reliability, which comes, the problem comes with, as cells with negative elements and so on. And the Cascade LP program is in fact a program which is running for low pass filters only. Since many of the cells have functionally equal variants, so performing the same function but have different structure, the HTML and the report files contain all variants, while the SPICE circuit description, the SPICE net list of the program, contains only one selected by the author of the RM software. Nevertheless, if not satisfied, the filter designer is expected to substitute this cell in the SPICE description by himself based on the data given in .html file. The Cascade AP program performs synthesis of all pass circuits only, and the Cascade TR program starts with a low-pass synthesis and then performs circuit element transformation based on the proper transformation which is given for frequency domain, in order to obtain bandpass, high-pass, or bandstop filters. And in the case of filters synthesized as a filtering function extended by a corrector, so we have filter plus corrector, the user is expected to perform separate circuit synthesis of the selective and the all-pass part. If a SPICE description is needed for such a construct, the user may use the merger program, which concatenates the SPICE descriptions of the filter and corrector, and after minor accommodations, performs simulation of the overall circuit. Here is one example of a sixth-order filter having two zeros at the positive omega axis and one pair of complex zeros in the right-hand half of the complex plane. The passive LC cascade realization programs produce, as already mentioned, a report file containing all the phases of the synthesis process, HTML file, which is extension of the report file with having a schematic. All the cells are given with element values, and finally it contains SPICE code for frequency domain simulation, which may be easily transformed into time domain simulation with small intervention by the filter designer. Now we are going to the GMC or OTAC filters. First, we will talk about GMC filters, which are realized based on passive LC prototypes. These, in fact, are low-pass filter, and the program is named GMC LC. To produce a GMC filter, in this case, a cascaded LC prototype circuit is needed. The new filter is obtained by substitution of the inductors and transformers with equivalent GMC cells. The idea is based on the implementation of a special negative impedance converter named dye-writer. Here on the left-hand side is the schematic and the circuit equations or constitutive equations of a right circuit, and on the right-hand side is the grounded simulated inductor, which means that on the top line it is the inductor is connected, and the thick line is ground, and in between the capacitor, which is now substituting the inductor, which is the point, which is the goal of GMC to eliminate inductances from the circuit. The inductances are integrated inductances. They have bad performance both in area, silicon area, and also in Q factor, or they have parasitics, capacitance, and resistance. So we have in between the capacitor and the point where the inductor is connected, a generator which is converting. What is here interesting is that there is no DC connection from the through the inductor, which is usual for an ordinary inductor, but nevertheless these are high frequency circuit, and zeroth frequency is not expected to happen. And here are two more cells. This on the left-hand side is the simulating floating inductor. And on the right-hand side is simulated transformer. You can see that the transformer and the simulated inductor is topologically the same, only difference is the capacitor, which is omitted to produce the transformer. Here we have a cell which would produce a complex transmission 0. On the top part, one can see an inductor, which is substituted by a complicated cell, and so on, transformer and inductor. And as you can see, for this cell, one needs 12 transconductors, 12 operational transconductance amplifier to be realized for a pair of complex transmission zeros. Then we go to the second variant of GMC filter realization, which is parallel realization of a single and double phase GMC circuit. We will start with a generic cell, second order cell, which will be extensively used for parallel and also for cascade realization. The structure of a parallel connection is the same as for the active RC counterpart, so it will be not given here. But what we see on the left-hand side is a cell which, depending on the connection of the nodes V3 and V4, may become anything of a second order, starting with low pass and ending with band stop and high pass. Here is, as you can see, the transfer function of this cell, which is created by analysis of the circuit. And as you can see, if we put B equals 0 and A equals 0, we will get a low pass filter, and so on and so on. So depending on the values on the conductions, will be produced different cells. As for the parallel realization, we will need only a BICVAD which has a 0 on the real axis, which was the case for the parallel connection in RC circuits only. And this is the cell which will be extensively used in parallel realization GMC filters. And this is the summing of the GMC filter. Here, like the RC, active RC case, one can change the sign of the transconductor by simply interchanging the input terminals. And in that sense, there is no need for special additional processing which will change the sign to allow for proper summation. Here is the structure of the Polyphase filter. The idea is to have two signals, I and Q, and they are processed in parallel, which means there are two identical filters processing the I and Q signal, which in fact, are mutually coupled to allow for the shifting of the passband on the omega axis. In that way, one can produce a filter function which is translated on the omega axis and has a high attenuation for negative frequencies, which is not the case with the ordinary filters. On the top line above, a notion of the transformation is given for the case of low pass, single pole or first order transfer function. So as we can see on the right hand side, on the top, omega is shifted by omega 0. After manipulating this expression, or one can get that in this way, the new transfer function, which is here denoted by BP bandpass, which what is the filter becomes, will have complex coefficients. It will be the first coefficient will be 1 plus j multiplied 1 minus j multiplied by omega 0 over omega c. There are no synthesis procedures which will synthesize circuits with complex coefficients. So the transformation may be implemented only on circuit level as is shown below. So in the next line we have on the left hand side a capacitor in a low pass in the original circuit. And what is on the right hand side? We have this capacitor to which is a signal brought which is first shifted for 90 degrees, that is J, and then multiplied by minus Gm. If Gm is equal to omega 0 C, then the transfer function of the bandpass circuit will be as above. Similarly, if the capacitor is floating, and procedure may be developed as shown here to produce a connection in between the I and Q, which is J and not J line. So the top line is I, the bottom is Q, because it is shifted by J. And this is a connection between the capacitors in the two chains or two filters which are processing the I and Q. And in that way, we are getting a two-phase filter. This is the first order cell now, which contains both channels. Top is the I, bottom is Q, and this is the in between is the connection between two cells. So a first order two-phase GMC cells arise. And in the similar way, second order two-phase cell may be used. The last program we will discuss is the GMC cascade program, which performs cascade realization of GMC filters. Here is the structure of the filter, which is fundamentally the same as the structure of the active RC, with the difference that here, in place of active RC, we have active GMC cells. Here is one example of a second order low-pass GMC cell, which is obtained by putting A and B equal to 0 and connecting the rest of the terminals properly according to the generic cell. As one can see here, and it will be discussed in the next slide, the output of this cell is connected to the output of a transconductance amplifier. Now, if so, the output impedance of the cell, which will be large, especially at lower frequencies. In that way, the transfer function of this cell may be affected if the succeeding cell in the cascade has finite input impedance. To avoid that, the GMC cascade program inserts a unity gain amplifier having finite input resistance at the having infinite input resistance at the input of all cells having finite input impedance. That is exemplified here for the case of the notch filter. As we can see, to the input impedance terminal denoted by VI, we have two capacitors connected, which would reduce the input impedance of the cell, and which will load the previous cell, which has a high impedance, and so the necessity of the unity gain amplifier is obvious. That was, of course, done for every single second and third order cell to avoid mutual coupling. Deliverables here are report file with complete information of the synthesis process, HTML file with complete information of the structure of the schematic and the synthesis process, and SPICE code for frequency domain simulation, which is, of course, suitable to be transformed into time domain simulation on will of the filter design. So that would be the end of part 2. I wish to thank you very much for your attention and patience.